Hello, welcome to another graduate video of Dr. Viv's. This is the 14th video, and we are at the halfway point in this series. So I thought it was appropriate for us to pause and consider how the equations we've been using for the past few videos even come about. The derivation of the Euler-Lagrange equations and the Hamiltonian equations of motion. So we will replicate the steps taken by Lagrange himself. He used the great virtual work principle of D'Alembert that had just come out, and seemingly out of nothing obtained his equations. It is considered one of the greatest intellectual feats of all time. And popularly, you hear authors talking about getting something for nothing, and we'll exactly see how that happens. It almost seems like a bunch of mathematical manipulations that if you do, you'll obtain significant results. Now, even though that is mind-boggling mathematics for its time, it is considered dated today. It is more appropriate for us to examine the derivation from a variational standpoint. Variational principles are the norm in physical theories today. In fact, if you want any theory to be taken seriously, you better have it as a variational principle. Variational principles exist for almost all theories, including general relativity and various quantum field theories and string theories. So we want to put everything in a variational setup and get the Euler-Lagrange equation. This was done by Euler. And then we'll use Hamilton's extremal action principle to obtain Hamilton's equations of motion. Along the way, I'll talk about the various relationships between these. And for simplicity, this entire video will be done with the understanding that constraints are already incorporated in the generalized coordinates. That is, you reduce the number of generalized coordinates consistent with the number of constraints in the problem. If constraints are not incorporated, then the Lagrange parameters will have to be used. It's not a big deal. It just takes a lot more effort, and it's a lot more technical. And I thought it would be better for us to consider the more basic treatment. So let's go to the first part of this video, which is using D'Alembert's principle, or the virtual work principle, to obtain Lagrange equation. So I'll just write D'Alembert implies Lagrange. So how does that happen? Let us fix our system first. We're going to have Qi to represent our generalized coordinates, where there are n particles. So if there are no constraints at all, then I will run from 1 to 3n. Why 3n? Because we are in 3 dimensions. So you have x, y, and z for each particle. And so there are going to be 3n coordinates, and we can work in a system of generalized coordinates q sub I. So for example, you can have q1 up to q3n if there are no constraints. If there are constraints, then let's assume there are k constraints. And these constraints have been enforced with the k Lagrange multipliers, and we obtain a reduced system of generalized coordinates. So the I now runs from 1 to 3n minus k. So if there are no constraints, then I runs from 1 to 3n. If there are k constraints, then I runs from 1 to 3n minus k. Now each particle has got a position vector Ri, where I here runs from 1 through 3n, 1 through n, because R with the vector sign means x, y, and z. So each of these particles has got a position vector Ri. This Ri is a function of the Qj and time, where j goes from either 1 to 3n or 1 to 3n minus k. So what we're going to now do is use D'Alembert's principle and create virtual displacements on the position vectors of these n particles. Each of these n particles now suffers a virtual displacement. The word virtual should be thought of as something like imaginary. It's not really there. It's a virtual displacement. So delta Ri is del Ri over del Qj, delta Qj. Now you may wonder, why has he not written the term del Ri over del T times delta T? These virtual displacements are supposed to occur instantaneously. They don't have any time evolution, okay? So no time taken for virtual displacements. So that's an important assumption we're making in D'Alembert's method. So our virtual displacements are given by that. And what about our virtual velocities? Well, the virtual velocities, Vi, of each particle is just the rate of change of the position vector, Ri dot. So using the mathematical principles known as chain rule, we can write this as del Ri over del Qj, Qj dot, plus del Ri over del T. Now these Qj dots are called the generalized velocities. It is important to note that the generalized velocities need not actually have units like meters per second, because these generalized coordinates can be anything. For example, they can be angles. In the double pendulum example, we saw that the generalized coordinates for the two angles from the vertical of each of the pendulums. So their theta dot would be angular velocity. But in general, it doesn't even have to have any recognizable shape to it. Now the virtual work. The virtual work delta W is given by the sum over all the i's of the net force acting on each particle, which I'll call F sub I, multiplied by the virtual displacement. So this can be very general. Each particle can have a special kind of force acting on it. And we're summing over all the i's, where I goes from 1 to n. So let's write down. Whenever I put a summation sign, it means I goes from 1 to capital N. I'll put the capital N here. If I don't write the summation sign and I simply use Einstein's summation over the repeated index, it means the repeated index is summed over either from I or j equals 1 to 3n, or I or j from 1 to 3n minus k if there are constraints. So that's the understanding here. All right, now we'll try to write this. Delta Ri is right there. So let's put it in here. So that gives me sum over all I, Fi dot del Ri by del Qj, delta Qj. This is what Lagrange called the generalized force. So this is Q sub j delta Qj. Where Q sub j is the is given by sum over all I, Fi dot del Ri over del Qj. Let me just be explicit about the summation sign, and j goes from 1 to 3n minus k, assuming the constraint case. So this is the jth component of the generalized force. As you can see, there are many components of the generalized force. Now we'll use the famous principle of D'Alembert known as the statics equals dynamics principle. So what does the statics equals dynamic principle say? It says that any dynamics problem can be viewed as a static problem if you think of the force as adjusted by subtracting the rate of change of momentum from it. So the principle is given by this: sum over all I, Fi minus Pi dot, that is dP by dt, the dot means time derivative, dotted with delta Ri equals 0. That is the virtual work principle. We will look at each of the terms, the first term and the second term, and see what we can do with it. So the first term is sum over all I, Fi dot delta Ri. Well, that, by our very definition, is Qj delta Qj. So that is done. Now we look at the second term. The second term will take a lot more effort to massage into the proper shape. So the second term, without the minus sign, is sigma I Pi dot, this dot is dot product, that dot is time derivative, delta Ri. And now we can write what Pi is. Pi is just, this dot is d by dt. So d by dt of the momentum, which is mi vi, dotted with the position virtual displacements, delta Ri. Now the virtual displacements are right there. So I'm going to copy that down. And meanwhile, the masses do not change with time. So when I differentiate, I'll just get the rate of change of velocity. But velocity vi is just written as Ri dot. So the rate of change of velocity is going to be the acceleration. So I'm going to get sum over all I, mi Ri double dot, dotted with, I'm writing this delta Ri here, from here, del Ri over del Qj, delta Qj. Observe the dot product acts on this and that. Okay, so we have now got this wonderful looking equation, and we're going to try to write this as something really interesting. So this is where the genius of Lagrange comes in. He manipulates this to get the Euler-Lagrange equations. So this can be written as d by dt of the whole thing minus a term. So what if I wrote it like this? Well, let's look at this. When I take the d by dt of the first term, I get that. And then I don't do anything to this. And then the second term, if I differentiate the second term, I get this, and then a derivative of the second term. So that I have to subtract. So I'm going to get minus mri dot d by dt of del Ri over del Qj. Actually, you know what? I'm going to look at just this part without the delta Qj. So let me write what I'm looking at here. This is just sum over mi Ri double dot times del Ri over del Qj. Just that part. What is just that part? Because I don't want to keep writing this delta Qj each time. So just that part is equal to what I wrote. Let me finish this. Okay, so if I differentiate the first term, I get that. And then if I differentiate the second term, I get this, but there's that term with a negative sign, so they cancel out. So no harm's been done. So let me just call this equation, this important step, I'll call this important step by the symbol star. Come back to star. Okay. Now we are going to write this term as something else. So let's write that. But d by dt of del Ri over del Qj, what is that? Well, that, by the rules of partial derivatives, is the rate of change of Ri with respect to Qj with respect to Qk times dQk by dt. So that's going to be Qk dot. Plus, remember, Ri is a function of Qj and time. So we also have to differentiate with respect to time next. So I get del to Ri over del Qj, del t, and then I get dt by dt, which is 1, so I won't write that. Okay. Now separately, let's write down what Ri dot is. Ri dot, which is shorthand for dRi by dt, because Ri depends on Qj and t, this is going to be del Ri over del Qk, Qk dot, plus del Ri over del t. The summation index, summation convention of Einstein is used here for k and here too. I'm going to call this equation star and this equation star, asterisk, and this equation cross. All right, now let's look at, from this equation, it's very clear. If I take the, okay, let me do another step. Del by del Qj of dRi by dt. So there's this equation I have, dRi by dt. Now I'll take del by del Qj of this. Now why am I doing that? You'll soon see. So this is given by del 2, because of the first term. I'll have to take the derivative with respect to Qj. I'll take the derivative first with respect to the first term and then with respect to the second term. So I get del 2 Ri over del Qk, del Qj, Qk dot, because I have the Qk dot unharmed, plus del 2 Ri over del T, del Qj. I'll call this double star. The interesting thing is to compare star and double star. The right-hand sides of star and double star are actually equal. I keep saying star, I mean asterisk. Why are they equal? These are mixed partials. Mixed partials always commute whenever the functions are at least twice differentiable. And these, we are assuming that these functions are all twice differentiable. When you write the particle's position vector in terms of the generalized coordinate, we are going to assume those transformations are at least C2. So we can invoke what's known as Claro's theorem from partial derivative theory. Because the right-hand sides are equal, therefore the left-hand sides are equal. We have arrived at an important moment, and that is this: d by dt of del Ri by del Qj, this term here, can be written as del by del Qj of dRi by dt. But dRi by dt is just Ri dot. So this can be written as del by del Qj of Ri dot. So let's just keep that there. Now from the equation known as dagger, we can actually find out what del Ri dot over del Qj is. So from dagger, I have del Ri, Ri dot, So Ri dot is all of this. So del Ri dot over del Qk dot. Well, Qk dot, there's only one term with Qk dot, and that is here. Qk dot will not appear in the Ri's because Ri is a function of only the generalized coordinates and time. It doesn't, Ri is not a function of the generalized velocities. So this is where we are going to make the assumption the constraints are holonomic. If you have only holonomic constraints, the only term with generalized velocities is this term. So this gives me del Ri over del Qk. So all this is to prove that the rate of change of generalized velocity with respect to the of the regular velocity with respect to the generalized velocity is the same as rate of change of regular position with respect to the generalized position. It's an amazing equation, but this is all the trouble we had to go through to prove it. Now, based on that, the second term can be simplified. So I'm going to write this term, I'll write the equation known as star as follows. What's on the left, I'll repeat on this side. So sum of mi Ri double dot dotted with del Ri over del Qj is equal to the sum over all I from 1 to n d by dt. The first term is untouched, mri dot dotted with del Ri. Now here, del Ri by del Qk, I'm going to write it like that. So that's going to be del Ri dot over del Qj dot. Okay, the second term minus mri dot dotted with, now d by dt, it can be written as that, and that can be written as that. Okay, so this is going to be del by del q j of Ri dot. So that's where we've got so far. Now, let's look at this term. The first term that we have is actually a kinetic energy-like term. So I'm going to write the, let me do one more step. The left-hand side, which is sum from I from 1 to n, mi Ri double dot, dotted with del Ri over del Qj is equal to, this first term can be written as del by del Qj dot of 1/2 mi Ri dot squared. Now let's just see if that's true. When I differentiate r square, I'm going to get a 2, which will cancel with this 1/2. So I'm going to get 2r dot, which is there, Ri dot. And then I'll have to take the derivative of Ri dot with respect to Qj dot. And that's exactly what I have here. So I do get that term. And I'll write the second term in also the same fashion. Minus the second term is going to be del by del Qj dot, just Qj, not Qj dot, of sum 1/2 mi Ri dot squared. Let's see if that makes sense. So the summation sign blesses both terms. So, and the same over here, the summation sign is over both terms. Let's see if that makes sense. If I take the del by del Qj inside and differentiate, that 2 will cancel the halves. So first term, I'm going to get Ri dot, which is right here, dotted with del Ri dot over del Qj, which is exactly that. So we get everything nicely. And at this point, you simply recognize that the particle's kinetic energy can be recognized. The kinetic energy of the entire assembly of particles is simply I from 1 to n of 1/2 mi Ri dot squared. So we're going to indicate that and put it back into that equation. So our final step is sum over all the i's, mi, acceleration dotted with del Ri over del Qj is just going to be d by dt so that here, I should have written d by dt over here. I did not write d by dt. Okay, it's d by dt there. And over the first term, because the d by dt is still there. I was only writing the this term as del by del Qj of kinetic energy, but the d by dt is still outside. So that's d by dt of del T over del Qj dot minus del T over del Qj. All right, so that's looking a lot like Euler-Lagrange already. So now what we're going to do is we're going to put this back in D'Alembert's principle. So this is the principle we indicated over here. It is that one. So put back in D'Alembert. The first term, which is this, the first term is that, the second term is this, but it doesn't matter if I call, because of the minus sign can be taken outside, so I'll put the second term first, okay? So I get d by dt, sum over all the i's, of del T over del Qj dot minus del T over del Qj, and sum over all the j's, and not i's anymore. So that is the second term written first. Okay, because I wrote the second term first, then I have to subtract it with what Fi is. But Fi dot delta Ri is just Qj delta Qj. So that's going to be minus Qj delta Qj equals 0. And that is j equals 1 to 3n minus k. And because this is true for all virtual displacements in the generalized coordinates delta Qj, it has to be true for each one of them separately. So we have our famous equation, d by dt of del T over del Qj dot minus del T over del Qj equals Qj, the jth component of the generalized force. So this is the legendary derivation that Lagrange performed in his famous book known as Mécanique Analytique. And it is widely regarded as one of the greatest derivations of all time. You get something from nothing. And what a something it is. It is at the heart of everything in physics. And these are sometimes called the equations of motion of the second kind. The equations of motion of the second kind are actually more general than the equations people usually use in even graduate school. So the equation that's commonly used is simply called the Euler-Lagrange equation, and that is a special case. So our first part of the problem is finished. We have obtained Lagrange's equations of motion of the second kind, hence obtain the Euler-Lagrange equations of motion. How do we get that? The Euler-Lagrange equation of motion is a baby case of the Lagrange equation of motion of the second kind for the case where the forces acting on each particle are conservative. So we are going to assume there exists a global conservative potential. And so the force acting is given like that. So this is a conservative form. Furthermore, we'll assume there's a single conservative potential for all the particles. You can make up a very complicated potential that will be enough for all the particles. So that's the assumption we're making. And I now runs only from the 1, 2, and 3. So you don't really have more terms than that. So now the Qj will become Fi dotted with del Ri over del Qj. All right, so let's look at this. I'm sorry, I made a misstatement there. The V's can depend on all of the coordinates. So V can be a function of all of the Ri's and time, possibly. So it can depend on all of the particles' positions. So these I can go from 1 to 3n, and J goes from 1 to 3n minus k. So let's just repeat that. So I goes from 1 to n, and J goes from 1 to 3n minus k, where k is the number of constraints. Okay, let's now write this down. That is the generalized force, jth component. What can this be written as? In terms of x, y, and z, I can write this as Fix times, so I'm breaking down the dot product, del xi over del qj plus Fiy times del yi over del qj plus Fiz del zi over del qj. Now, because I've written the force in that form, I can use that. So I get qj equals negative del v over del xi, that's what Fix is, times del xi over del qj minus del v over del yi, del yi over del qj, and the same thing for z. Now there's a theorem called Euler's theorem in partial derivatives, which tells you this is equal to simply negative del v by del qj. Right here, Euler's theorem. Because qj is simply negative del v by del qj, we can put that over there. Meanwhile, I'm going to write this Euler-Lagrange, the equation of motion of the second kind, as follows. I'm going to write it as d by dt. Observe what I'm doing. Del of t minus v over del qj dot minus del t minus v del qj equals 0. So what I've done, this term is a more important one. What I've done is I've taken the negative del v by del qj on the right side and brought it to the left, okay, where it becomes positive, and indeed negative of a negative is positive. So I brought it to the left. Here, no harm done, because v does not depend on velocities. Because v does not depend on velocities, only positions, it will contribute nothing when you put that there. But of course, t minus v is precisely the Lagrangian, so we get d by dt del L over del qj dot minus del L over del qj equal to 0. These are famously referred to as simply the Euler-Lagrange equations. The second half of our video is to obtain the Euler-Lagrange equations using what are called Euler equations. Now, Euler was not quite interested in physics as much as mathematics. He was interested in problems involving the minimization of surfaces and things like that, soap film and things of that nature. So Euler was using what's known as Fermat's extremal principle and creating a mathematical tool known as calculus of variations from it. So the second half of our video will be on the calculus of variations. Then you can apply it to a specific system known as a mechanical system and get the Euler-Lagrange equations. But Euler's theory is much bigger than that, and it's used in, as I said, not only in all theories of physics, but also in things like differential geometry and algebraic geometry and so forth. So it's a very big tool. So the second half of our video will explore the variational principle side of this problem. So we're going to start from a variational principle, derive the Euler equations of motion, which are separate. And from that, we'll get the same Euler-Lagrange we got here. And then we'll also use it to obtain the Hamiltonian equations. So that's going to be the second part of this video. So we're going to start by introducing a new branch of mathematics, and that is called functionals and the derivatives associated to functionals. So what functions do, let's recall, functions take numbers and map it to other numbers. So for example, if you have the temperature, it's a function in three-dimensional space. It's a scalar function. You take any point with x, y, z coordinates and convert it into a thermometer reading. That's what a function does. What does a functional do? A functional maps an entire function into a real number, okay? So it maps the entire functions into real numbers. So what we're going to do is we're going to use some mathematical notation here. So if I write a single function f acting on a manifold M, then f takes points in M to the real number. That's a real function. Now, the space of all functions on the real functions, or you assemble all the real functions possible on a manifold. Manifold just means a general space. So if you take the space of all real functions, it's going to be an infinite dimensional space known as C infinity M. That infinity stands not for the fact that it's infinite dimensional, but rather that it's infinitely smooth. So we're only going to look at smooth real functions for this exercise, even though you don't really need smooth. It's enough for second or third derivative to exist. We'll, for simplicity, consider it to be smooth. So you take the space of all real functions, and your functional, which I'll call G, takes you from the space of all functions to the reals. So this is what I mean when I say a functional maps entire functions to real numbers. So what is the appearance of a functional? It looks like this. G consumes the function f as follows. So to define the functional, I have to tell you how it eats the function and spits out a real number. So currently it's chewing on that function. Let us see what's going on inside its guts. That is I to f, some other function f of f dx. Now when I write f of f, I mean that it can be f of f, f prime, any number of derivatives, and time. So that's my convenient shorthand. When I write f of f, it can depend on not only the function, but also the nth derivative of the function as well as time. Okay, so that is our setup here. And so I've defined not only the functional, but the functional has got the stomach of the functional is this capital F, which is digesting not only the function, but all its derivatives and time. Well, I shouldn't write time, I should write X, because we are in the domain of space, not time. Okay, so that's the most general functional. Now we're going to define the concept of a tangent vector of a functional. Now that can be defined in terms of what's known as a Frechet derivative. put an accent over the E if you like. So the Frechet derivative, sometimes called the functional derivative, is defined as follows. The functional derivative of G with respect to vectors, which are themselves functions in the space of all smooth functions on the manifold. So what is it? I'm going to define this object. It's a linear map written like this: delta G F, and that's eating the vector. So when you put a delta in front, you've created a hungry object known as a Frechet derivative, and so it has to be satisfied. The hunger is satisfied by feeding it a vector in quotes, because the vector is just another function. And this takes you from C infinity M to C infinity M. In other words, it takes you from functions to functions rather than from functions to real numbers. Okay, and how is a real map? I've still not defined it. That's the domain and the range, with a specific condition that H at the initial point, these are called initial and final points. H initial is the same as H final, and now I'll define it. The definition is this: delta G F H is the integral from I to F, d by d epsilon, epsilon equal to 0. So it's the derivative with respect to some parameter epsilon, evaluated when epsilon is not moving, or when epsilon is 0, of f plus epsilon h dx. So it might be a good idea to draw a figure to understand some of what's happening. This is the subject of variational calculus. So I'm going to draw my manifold M. In general, it can be a manifold with any number of holes, like a donut, for example. And then you have your initial point and you have your final point. Okay, you join them up by some path. You look at nearby paths. So you're going to get an entire bunch of paths. In fact, infinite number of paths between some initial and final points. Okay, in this direction, you have the derivative with respect to epsilon governing which path, your movement across the paths. And in this direction, del by del x gives you the movement along each path. All right, so that's roughly what's happening here. All right, so this general setup on the manifold level can also be looked at in a slightly different way. We're going to consider the space of all paths. The space of all paths is called omega, and it depends on the initial point, the final point, as well as the manifold. Now, in that space, you're going to have the point I, the point F, and the path we're going to seek is this optimum path known as gamma naught. That's the path we want to seek. That is the solution to any problem. I have not specified the problem, but it could be something like the minimal surface or the geodesic, the path of an airplane flying from one city to another city. And around that are paths which are not optimum. So these paths that are not optimum are going to be differing from the optimum path by some vector eta. The same vector we're thinking of, the h vector is now eta, that describes a deviation of the not so optimal path gamma from the optimal path gamma naught. So our problem is to seek curves which set the variation equal to 0. Now, the problem of setting the variation or the Frechet derivative equal to 0 is called Fermat's problem or Fermat's principle. Pierre Fermat was a scientist. He was actually a lawyer who did science on the side. And he was interested in trying to explain how light behaves. So he showed that light behaves in such a way that this action, which he called the action, is the Frechet derivative of that is equal to 0. People sometimes mistakenly say light follows the path of least time. It's all we need is the Frechet derivative to be 0. It need not be least. It can be maximum, minimum, or neither maximum nor minimum. So Fermat's principle says the Frechet derivative vanishes. Let us use the Fermat principle to derive the famous Euler equations. Now, this is another instance of getting something from nothing, although the machinery here is considerably more sophisticated. For example, this is, generally speaking, a n-dimensional manifold, and this is an infinite dimensional vector space. And we're not going to concern ourselves with the details of this mathematics. It's kind of beyond the scope of even a graduate course. But I will just content myself with the bare bones derivation. So we're going to, for simplicity, we'll take the manifold to simply be R2. The simplest setting. We can easily generalize later. And then the curves gamma will then be y equals y simply as a function of x. This is just a graph. If m is R2, you have the y-axis and the x-axis. It's just going to be some curve you're looking at. So that's going to be the functions f. Now we're going to look at our s. S is like g, our functional. Our functional is a function of each of these curves. And it's given by the integral from I to f, some random function, capital F, and we'll now specify what it's a function of, y prime, x, dx. Now I stuck to just the first derivative because that's all Euler wanted. But if you want the second derivative, you can put the second derivative too. It'll be a more complicated result. But this is what Euler had, and that's what I'm going to do. Gamma naught is the optimum path we seek, such that delta S equals 0, and gamma is just another path. So we're going to write gamma naught as y as a function of x. That's our object of desire. And gamma is the object of desire plus epsilon times eta as a function of x, where epsilon is some real number. That epsilon is what we're going to differentiate against to get the Frechet derivative or the functional derivative. Now, by our conditions, the path space goes from I to f with I and f fixed, which means that eta should vanish at both I and f. So the condition that we have to have is that eta I equals eta f equals 0. All right, now we're going to define the famous, we're going to write the S of gamma. S of gamma is the integral from I to f. Because S of gamma goes away from the path y, we have to write f of y plus epsilon eta, y prime plus epsilon eta prime, x dx. So that is S of, this one here is S of gamma naught. and that's S of gamma. Now, the Fermat principle is the Frechet derivative vanishes. Another way of saying that is small variations in the functional from the sought path will have zero variation. Okay, so now we'll use Fermat's principle. The Frechet, Fermat said it like this. Fermat said nature follows the path of extremal S. In our language, it means the Frechet derivative is zero. So now we'll, by the way, this is the important comment I said, it's extremal, it's not maximum or minimum, it's extremal. Okay, it can be either maximum or minimum or even neither. What I mean by neither? You all know that equilibrium can be of three types. You can either have unstable equilibrium, or you can have stable equilibrium, or you can have neutral equilibrium. So all three things are equilibrium. That's what I mean by neither. All right, now let's get busy with this. The Frechet derivative has to be zero, so zero equals delta S. Let's recall the form of the Frechet derivative. It is this one here, delta S gamma eta, which is the integral from I to F, d by d epsilon of evaluated at epsilon equal to zero. I'm just following the prescription of F y plus epsilon eta y prime plus epsilon eta prime x dx. So I have, all I've got to do is do that derivative, and that's just fairly simple. So let's do that next. So I get zero equals integral from I to F. The derivative with respect to epsilon by the chain rule is just del F by del y times dy by d epsilon, dy plus epsilon eta. So this is y plus epsilon eta, but it's at epsilon equal to zero. So I put that epsilon equal to zero already. Maybe just for the first time, I'll be more careful about this. Y plus epsilon eta at epsilon equal to zero times dy plus epsilon eta over d epsilon. That's what I really have at epsilon equal to zero plus del F over del y prime plus epsilon eta prime evaluated at epsilon equal to zero times dy prime plus epsilon eta prime over d epsilon evaluated at epsilon equal to zero times dx, the whole thing. So that's really what I've done. It's the chain rule. All right, now I'm going to have to there's a key step next. Before the key step, let me just let the dust settle a little bit. When epsilon equal to zero, this term vanishes. So I just get del F over del Y. And here, the rate of change of Y plus epsilon eta over epsilon is just eta. Plus del F over del Y prime times eta prime dx. So that's a very nice looking object, but we can't do anything with it because of this eta and eta prime, two different things. Eta is completely arbitrary and describes a variation in the path. Now, keeping in mind that eta is completely arbitrary, you can't make any assumptions about eta. That's the reason why we do the next step. This next step is a key step in almost every calculus of variation problem, no matter how sophisticated. Now, once you get into mathematics, you have all these variational principles in functional analysis, in differential geometry, in non-standard Riemannian geometry. There's all kinds of sophistication that will come in here, and you can't even recognize it as an action principle. But there's always one key step that's common to all of them. In all action principles, no matter how deep or strange the action principle, you have to use the integration by parts to bring global data into local behavior. So use integration by parts, which I'll abbreviate IBP, to relate global to local. Let's see how that works out. Well, I can write this as I to F. The first term I'll leave unchanged. The second term I'm going to write as d by dx of del F over del Y prime. Just bear with me for a moment, and you'll see why that's true. And then I'll add a term, I to F, d by dx of del F over del Y prime times eta dx. So what has happened here? It's actually very simple. This term has got two terms. The first term is just that, okay? That gets canceled out. The second term is just this. So I've done nothing strange. This can be written as d by dx of del F by del Y prime times eta plus del F by del Y prime times eta prime by the product rule of Leibniz. This will cancel with that. That will survive, and that is exactly what we have. So nothing illegal. Now, the beauty of this term is it's a pure boundary term. By the fundamental theorem of calculus, the integral of a pure, because it's d by dx of dx, can be written as, so this term here, which I'll call the boundary term, BDRY means boundary. So the boundary term looks like this, I to F, d of del F over del Y prime times eta. And by the fundamental theorem of calculus, that's what FTC means, this is just the del F by del Y prime eta evaluated at F minus del F by del Y prime eta evaluated at I. So in fact, you can have more general variations where all you demand is that this term is equal to that term. But since we have assumed that eta I equals eta F, it is definitely true. But in general, you can be a little more general than that. Okay, so this is equal to 0. All right, it is equal to 0. Now, all we have to do is worry about that. Now that is equal to 0, but what does that really mean that this quantity in the brackets is equal to 0? That's what we really want to have, but is that true? There is a theorem known as the Hilbert's bump function lemma, which I will prove at the end of this video, and which states that that is indeed true. Okay, so we have del F over del Y minus d by dx of del F over del Y prime equal to 0. These are the famous Euler equations. So I have derived the Euler equations of motion. Now I'm at this part now, and hence the Euler-Lagrange equations of motion. Okay, so how do I get the Euler-Lagrange equations of motion? Well, for that, I just have to move my system to the configuration space, that's all. So let me, instead of F, I'm going to replace F with the Lagrangian L, which is a function of Qi, Qi dot, and T. So that's the kinetic energy term, which is a function of Qi, Qi dot, T, minus a potential energy term, which is generally a function of just Qi and T. no velocities. So that's the setup we have. So we're going to use the analog of Fermat's principle in the subject of mechanics, which is called Hamilton's principle. So let's write down the action as Qi is the optimum path that we seek. So that's going to be the integral. Now I won't use I and F because I is taken by the subscript for the generalized coordinates. So I'll write 1 and 2 instead. So L of Qi dot t dt. All right. So I just want to point out this is called the action in physics. And the units of S are always going to be angular momentum. In other words, it's going to be joule seconds. In early days of quantum theory, this was a very important quantity because one surefire way of going from classical mechanics to quantum mechanics was to do what's called the closed orbit quantization. So they would take the integral over a closed oriented orbit, pi dqi, and pi has got p dq has got units of action because the momentum times distance is angular momentum. And this was set equal to Planck's constant times some integer n, where n equals 1, 2, 3, etc. This was how quantization was enforced in the old days. This is called the Bohr-Sommerfeld quantization. So we are back in the old days of quantum mechanics. And so that's where the term action comes in. So when I keep saying the word action, you should realize that it's a physicist in me that remembers these old pioneering days. So by Fermat's principle, let's come back to this now. So by Fermat's principle, we should have delta S of Qi of eta I equal to 0. So I'm imagining the exact same thing except in a much bigger space. Instead of R2, I have R to the power 3n minus k. Okay, so really big space. So I goes from 1 to 3n minus k here. Very many equations. And eta I, so each of these Qi's is perturbed to Qi plus epsilon eta I. So you can imagine the generality of the problem. It's pretty general. So I get the exact same thing with L replacing the function f and Qi replacing the function y. So I end up getting, therefore, del L by del Qi minus x replaced by time. So I get d by dt of del L over del Qi dot equal to 0. So Euler's equations applied to the Lagrangian is what makes this called the Euler-Lagrange equations. So we come a full circle. The Euler-Lagrange equations, which we got from a terrifyingly opaque principle known as the virtual work principle, and specialized for a specific kind of generalized force, which is pure potential, gave us this equation, and we got the same equation from a completely different standpoint known as the variational calculus principles of Euler and Fermat and Hamilton. The final portion of our video is to use Hamilton's extremal action principle to obtain Hamilton's equations of motion. And then I will also prove or indicate the proof without really going into the details of the bump function lemma of Hilbert that we used. So that's what remains. So let's go on to the next part, which is Hamilton's principle. Hamilton's principle is really the same as Fermat's principle applied to mechanics. That's all it is. So it says the Euler-Lagrange equations give the same information as the equations of motion of the second kind. In other words, you can get everything from action principles. Okay, that Hamilton's action principle is a name that has stuck, but it really is no different than Fermat's principle. So I feel a little bit loyal to Fermat, and I feel like downplaying Hamilton's principle. But we're now going to use Hamilton's principle to get the famous Hamilton equations. So the setting for Hamilton's equation is we are now in the space known as phase space. Okay. Phase space has got coordinates and momenta. So typically have momenta and then the coordinates q. There are n of these and n of these. So it's a 2 n-dimensional space. Now, the way it works is if you have a manifold of dimension m, this 2 n-dimensional space is actually the cotangent bundle of the manifold T star m. So at each point, there's a q and there's a momentum vector attached to it. That is how it works, okay? So the path space we have is omega of T star m between the points initial and final. So if you remember, I drew a little sketch here. The path space depends on the manifold and the initial and the final points. So now the manifold has been broadened to be the cotangent bundle. So I would like to draw a schematic figure to go with this. 1/2 your data is taken from the momentum space and 1/2 your data is taken from the position space of the phase space. So we'll draw a crude sketch. Okay, so that is supposed to be, they're supposed to be somehow perpendicular to each other, even though perpendicularity has no real meaning in all this. But the path that you really are seeking is your path gamma naught, and any other path is a deviation on the gamma naught. The deviation is going to have two components. The component in the tangent space, cotangent space at any point, which I'll call x, and then the m itself at that point x. Actually, it's a tangent space, but I'll just call it m at the point x. So in the cotangent space, the vector that I will have, I'll call that vector by the symbol zeta. And in the tangent space, the vector I'll have, I'll call by the vector eta. Eta is the same as the vector we had before. So now we're going to have a double variation, double Frechet derivative, if you like. So, but just to keep things simple, I'll treat it as a single Frechet derivative. In principle, you can have two independent parameters, epsilon1 and epsilon2. Some authors use S and T as parameters, but I like to keep this even though it's an independent double variation, I will somehow make it a little bit more easy to swallow by thinking of it as a cojoint or conjoint variation. So we'll think of a two vector conjoint variation. But the word conjoint simply means that they're linked together by using the same parameter epsilon. All right. So now the Frechet derivative is going to be set equal to 0. So that's more complicated Frechet derivative for the Hamilton's principle. So what would that be? Now, first of all, I have to write the action. What is the Hamilton's action? Hamilton invented the following action. And this is why the principle is named after him in honor of Hamilton's action. S of PQ is the integral 1 to 2 of L dt. That's the basic definition. But what is Lagrangian? Lagrangian is formed like this. From time t1 to time t2, of P dot Q dot minus the Hamiltonian as a function of Q, P, and T. Observe, it's a Lagrangian that is more fundamental in the variational principles, not the Hamiltonian. So this is one place where the Hamiltonian takes a sidekick position to the Lagrangian. The Lagrangian is what's important, and that is what is inside the functional derivative. But you can write the Lagrangian in terms of the Hamiltonian using the prescription. Normally, we use this prescription to write the Hamiltonian in terms of the Lagrangian, but now we're going the other way around. We're writing the Lagrangian in terms of the Hamiltonian. Now we'll do the Frechet derivative. I won't write all of that, so I'll just write delta S equal to 0. And what does that give me? Integral from 1 to 2. Well, first of all, going through all the same steps that we went through earlier in getting the basic Euler equation, this sort of thing, you should imagine in your mind, I'm doing the same thing, but I'll only write the results at the end like this. So otherwise it's too much writing. So I'm going to get P dotted with eta dot plus, now here, I'll have zeta dotted with Q dot. So I'm by the product rule. And then, so here I'm also ignoring terms where with 2 epsilons. So you're going to get terms like that when terms of order epsilon squared are being ignored. And anyway, it'll be ignored because epsilon is set equal to 0 when you do the Frechet derivative. So you only get the first order terms like that. And then I get del H over del Q vector dotted with eta. So that's a column vector, that's a row vector, or row vector and column vector. You should think of all these as matrices. And then I get minus del H over del P dotted with zeta dt. Once again, we have to use a key step, which is integration by parts, to make this into something that we can work with. So that's the next thing we do. 0 equals the integral from 1 to 2. And the integration by parts is got as follows. I can write this as P dot eta, the whole thing dot. That's the first term. And to compensate for that sin, I have to subtract P dot eta. That's the term we don't have. So when I differentiate this, first term is going to be P dot eta, which will cancel this immediately. And the second term is going to be P dot eta dot, which is this. So I'm all good. The other terms I'll simply write plus zeta dot Q dot. And then these terms I'll simply copy again. Minus del H over del Q dot eta minus del H over del P dot zeta, the whole thing dt. Now, I forgot to mention that because of these variations occurring between 1 and 2, both zeta and eta have to satisfy the boundary conditions, and the boundary conditions I will write here. The boundary conditions are zeta at 1 equals 0 equals zeta at 2, and eta at time 1 equals 0 equals eta at time 2. So now we have those boundary conditions imposed, and so this total derivative term will simply be 0. So let me write one more step. This is going to be the integral of P dot eta rather, evaluated between 1 and 2. That goes to 0 because of these boundary conditions. And then I have plus the integral of 4 terms, these 4 terms. But observe that you have 2 terms with eta and 2 terms with zeta. I'll club them together. So I have zeta dotted with Q dot minus that one, del H by del P minus eta clubbed with those 2 terms. So I get P dot plus del H by del Q. the whole thing dt. And now we use the 2n dimensional version of the Hilbert's bump function lemma, which I'll abbreviate as BFL. Each of these terms will be 0. And so we get Q dot equals del H by del P. Those are the n equations of motion that recover the Legendre transformation. And then the other ones give that dynamical content in the problem with a minus sign. So that's a dynamical shell. We have in this manner obtained the famous set of equations known as Hamilton's equations. Well, the last part of this video is to indicate the proof of the bump function lemma. You see that this bump function lemma has been used quite a bit in extracting information from this Frechet derivative. How do you remove the protection of the integral sign and expose these to the savagery of the zero sign? Well, the answer is using the bump function lemma. So let us state the bump function lemma for a very simple case, and I'll leave the generalization of it to your imagination. So David Hilbert was a big deal in the early days of variational calculus. In fact, it is he who actually found the so-called, now it's called Einstein-Hilbert action, but it was entirely due to him. He found the action principle for general relativity, thereby giving it a very great status. So the bump function lemma is this. If you have a function g that is continuous, continuous functions are indicated as C naught, on some interval, closed interval AB, and the integral of g of x times some eta of x dx is 0 on that interval for all eta that is at least C2, which means second partial derivatives are continuous, and such that eta vanishes at both the initial and final points, then we have that g of x is identically 0 on AB. You can see that this answers every application that we have, ranging from the simplest one to the more advanced vector application. How do you prove the bump function lemma? The proof is very cute indeed. It's one of those proofs you'll never forget when you see it. So we'll assume that this is not true. What does that mean? We'll assume that even though a to b g of x eta of x dx is equal to 0, we have g of zeta is not 0. If it's not 0, it has to be either positive or negative. I like to be positive, generally speaking. So g of zeta is bigger than 0 on some subinterval c comma d, which is part of the main interval a comma b. So we're going to make that assumption. Even though this is 0, g is not 0. It's bigger than 0 on a small subinterval. Now let's look at that eta function. What we're going to do is we're going to create a bump function. So that is A, that is C, that is D, and that is B. So we're going to call our bump function eta, which we manufacture to be C2. So we have to manufacture a bump function that is C2. How do we do that? Well, first of all, eta is 0, where it doesn't matter, on AC and on here and here, dB. So those are garbage places because g of zeta, zeta comes from the interval CD. That's a problem interval. So it's only in the problem interval the bump comes up. So the bump is defined as follows: x minus c cubed times d minus x cubed on the interval CD. Now this actually has that pleasing shape that I wrote. Why do you choose this? The cube is there to make sure it's C2. It is differentiable twice and it vanishes at C and D. That's why the cube is there, okay? So this satisfies all the requirements, all the hypotheses on eta. It is C2 and it vanishes at A and B. That's definitely true because of the partial definition on AB and DB. AC and DB is that eta is 0, and it's C2 everywhere. So it satisfies. Now we're going to write the integral from A to B, g of x, eta of x dx, as a sum of 3 integrals. So it's going to be the integral from A to C, g of x, eta of x dx, plus the integral from C to D, same thing, plus the integral from D to B, last segment, g of x, eta of x dx. Now these are 0 because eta function is 0 there. However, by definition, between C and D, eta is positive. By hypothesis, by construction, our eta is also positive in that interval. So we have an integral from C to D of a positive quantity, dx, that is positive. But that contradicts our hypothesis. So we have arrived at a contradiction. Because of the contradiction, what we assumed cannot be true. Therefore, g of zeta must be equal to 0 on the interval C of D. And since C and D are arbitrary, on the entire interval A and B. That concludes the proof of the famous bump function lemma.